Hello, wonderful people. Here we are, last bit of the book, chapter 35, circuits. And what is a circuit? Any path along which electrons can flow is a circuit. And so electrons can flow anywhere, and they flow really easy through copper. And see, we got the plug over there. So the idea is we wrap the copper in rubber or plastic to keep the electrons inside. And uh, and now we've got a circuit, a path where the electrons are going where we want. What's happening? The clicker's not clicking. Click. There it goes. All right, there's a flashlight. There's 3 batteries in that flashlight. There's the little light bulb and the switch on the outside. And that's what makes it work. There are several ways to connect the battery and the bulb from a flashlight to light up the bulb. The important thing is that there must be a complete path for a circuit. It includes the bulb filament, the light bulb. It goes from the positive side of the battery and then returns to the negative side of the battery. Electrons flow from the battery through the wire into the bulb, then out of the bulb, and then through the wire back to the positive part of the battery. If all that's all lined up in a row, then current can flow and the light bulb will light. Here are some unsuccessful ways to light a light bulb. You've got a wire to the bottom of the light bulb in the first picture. In the second picture, they just add another wire. In the third picture, there are 2 wires, but they're both going to the same terminal. And in the fourth picture, the light bulb's between the wires, but the top of the light bulb is touched by the wire, the glass part. It needs to touch the metal part. So none of those will work. There's how you do it. The first one shows the wire on the bottom of the light bulb and the side of the light bulb. And then you can take away one wire so that in the second picture, the bottom of the light bulb touches the battery. And in the third picture of B, the side of the light bulb touches the battery and the wire touches the bottom of the light bulb. So let me show you a picture of a light bulb. The cartoon in the middle shows very nicely the way that the light bulb is made. And on the left is a picture of an actual flashlight bulb. And there you can see there's the metal on the outside. And then down here is the metal part also. And that is that metal that goes up into the filament. And then there's the filament, the coily part. And then back down through into the metal. So the electricity comes in the bottom, goes up through the filament, and then back and into the metal. So there's the bottom of the light bulb. You can see the metal on the bottom very clearly, and the rubber or plastic insulation between the two. And there's an ordinary screw-in light bulb with the same setup, metal in the center of the bottom, the insulation, and then the metal on the outside. So that's how a light bulb is. Oh, and incidentally, this part, that's called the filament. That's the part that heats up and glows white hot, and that's where the light comes from. In the old style light bulbs. New style light bulbs like these, well, there's a circuit in there and there's little LEDs. It's complicated. But the old style light bulbs like this, which you still see in flashlights all the time, that's all it is. A little filament that heats up and glows white hot. So let's talk about the flow of charge in a circuit. It is very much like the flow of water in a closed system of pipes. In a flashlight, the battery is like a pump. The wires are like the pipes. And the bulb is like, well, any device that operates by the water flow. If there's a valve in the line and you open the valve, then the pump is operating. You got to have water pressure. Then water in the pipe starts to flow as soon as the valve is opened. That's a fine analogy. And remember, the water and the electrons are already in the pipe. Okay. Something else to remember, Electrons do not pile up inside the bulb. The electrons come in here, they go up through the filament, and then they go down and around. So the electrons come in and go through and go out. They're not stuck inside there. They just flow. And it's the energy, it's the electrical energy that is being brought with the electrons that heats up this. The energy, electrical energy, turns into heat energy in the filament. Is that making sense? Great. So a circuit is any path along which electrons can flow. And a gap in the circuit is a switch. And if you open the switch, then current won't flow. And if you shut the switch, then current can flow. That is true over there with the parrot. Edison tried 6,000 things that didn't work before he got tungsten, which is a very rare element to come across. My favorite thing that he tried was a hair off of the beard of his assistant. Yep, plucked the hair, put it in there just to see if it would work. It didn't. Okay, that water analogy, that one there. That is not true in a couple ways. One, if you have a break in a pipe, then water comes out of the pipe. But water can still flow through the pipe, but not an electrical circuit. If you have an electric circuit and there's a cut in the wire and you touch that to copper to something that goes to ground, then the electricity, the electrons just go straight to ground. Also, if you open a water valve, you have current flow, but for switches, you have to shut the switch. So that's kind of opposite. Oh yes, series and parallel. So most circuits, especially in the house, have more than one device that receives electrical energy. These devices are commonly connected in the circuit in one of two ways, series or parallel. And we're going to talk a bunch about that. So there is a picture of a battery, then in the picture on the left, it comes out of the battery and it goes to the switch. And you can see the switch is made of copper and it's open. Then the wire goes to the first light, then the second light, then the third light. And then it goes back to the battery. And then in the cartoon picture on the right is the picture of the exact same thing that we set up in the lab. Okay, does that make sense? So if you shut the switch, all three lights are going to come on, right? This is what we call a series circuit. The current flows through each one in turn. So all the current goes through the switch, then all the current goes through the first light bulb, all the current goes through the second light bulb, then all the current goes through the third light bulb. Yeah, so that's what makes a series circuit. So if there's one break in the wire, one switch, all three lights go out. Also, third sentence there. Burning out one of the lamps will turn off all the lamps. So when I was a little kid, we got the cheap Christmas lights, and if one bulb burned out, then the whole string burned out, and that's what's set up here. So if one of those light bulbs burned out and there's no current flow, then the other two lights are also going to be off. That's good. And that's the main disadvantage. First sentence. The main disadvantage of a series circuit is that when one device fails, the current in the whole circuit stops. Some cheap light strings, like when I was a little kid, are connected in series. When one lamp burns out, you have to replace that one light bulb or no lights work. I like what the mouse says. A series circuit is like a single lane road with no alternate path. If there's a roadblock or a cave-in, traffic will stop. True that. All right, here's a question. What happens to the light intensity of each lamp in a series circuit when more lamps are added to the circuit? So, the addition of more lamps results in greater circuit resistance, and this decreases the current in the circuit. So if the current goes down, then each lamp gets less less bright. So all the lamps get a little bit more dim if you add more light bulbs. Because remember, each light bulb has resistance in it. All right, now we're going on to the other half of the circuits, parallel circuits. Now, let's look at the picture on the left. You've got the wire coming out of the battery, and then right here, it breaks off into 3 separate directions. And each one of those has a switch, then a light bulb, and then they all come back together. So now, and then that comes back and goes to the battery, so there's a complete path for current to flow if the switch is shut. These 2 switches are shut, and that light is on. This one's open, so that light is off. And we've got the exact same thing over here. They even have little switches drawn in the cartoon. See that? Very cute. Does that make sense? You might need to study that for a moment. Hit pause if you need to. What is a parallel path for current to flow? That's what we call a parallel circuit. What is a parallel circuit? All right, this is a great little cartoon. So there's the old physics professor, older than me. He's bald. And he says, I'm going to extend the terminals of this 12-volt battery with this pair of metal rods. And he puts them in. A lamp will glow just as bright when connected here, at the bottom of the rods, as here. And the students think to themselves, of course, it's still 12 volts. And that makes sense. No matter where you slide that light up and down, it's going to be the same brightness. Then he says, now I fasten another identical lamp. What happens to the brightness of the first? And everybody thinks it's the same. You can put a bunch of lights in there, and the brightness of each lamp will still be the same. And that's what he says. Same brightness because 12 volts is across each. That's what I said. And a third lamp also, same brightness. Well, why not? There's still 12 volts across each lamp. So then he says, how does the battery know to supply 3 times as much current to 3 lamps? That's a good question. How does the battery know to supply 3 times as much current to 3 lamps? And then the somewhat bald kid says, I know. With 3 separate paths, the battery has 1/3 the resistance between its terminals. That's why it delivers 3 times as much current for its 12 volts. And that is very well said, very correct, and a little bit hard to understand if this is all new to you. Very good. But doesn't this mean the battery is putting out 3 times as much energy as when lighting only one lamp? And then the same guy says, yes, and you can expect the battery to wear down 3 times as fast. Such excellence. Okay, I'm not so worried about the resistance between the terminals. We're not going to get into that. We only have 2 days left of school. All I'm asking you to understand is that if there's 12 volts on this from this pole to this pole, and you put a lamp in there, it's going to glow with the same brightness, no matter how many you put in there. And we'll leave it at that. In a parallel circuit having 3 lamps, each electric device has its own path from one terminal of the battery to the other. True. There are separate pathways for current, one through each lamp. True. In contrast to a series circuit, the parallel circuit is completed whether all 2 or 1 or all 3 lamps is lit. A break in any one path does not interrupt the flow of electricity in the other paths. That's a bit much. That's a bit much. There's the review question. What happens to the light intensity of each lamp in a parallel circuit when more lamps are added in parallel to the circuit? Think, think, think. 3, 2, 1. The light intensity for each lamp is unchanged as other lamps are introduced or removed. Changes of resistance, skip that. The light intensity for each lamp is unchanged. That's the answer. There is schematics, and we're going to save that for tomorrow. So we'll end there. Parallel circuits. That little cartoon's very helpful. I'll put that in the notes. There's the picture. Series circuits. There's the picture. And what is a light bulb? How does the light bulb work? You've got the metal on the bottom, and the metal on the sides, and current goes through. Okay? Is that good for you? That's good for me. Thank you so much. Good luck. Bye-bye.